Hello everyone, welcome to week 11 of nptel analog communication problem solving session. So today we will be solving problems on topics that have been taught in week 11 of nptel analog communication. So in the week 11, the figure of emphasis filter, pre-emphasis filter, de-emphasis filter and figure of merit has been taught. So it is kind of advanced FMI, I can say. So we will just open the courses, check the exact topics. Okay, so as we can see that in week 11 the topic was FM noise analysis. So today we will be doing FM noise analysis. So figure of merit we have done in the context of amplitude modulation and general communication. Now we will be doing the noise analysis with respect to FM specifically. So let us take the noise analysis of FM. So there is a carrier signal. There is a carrier signal which is AC cos omega ct, and then there is a noise signal. That noise signal has a amplitude I and a frequency which is different from omega c. So let's write it as omega c plus omega t. So the received signal is AC cos omega ct plus I cos omega c plus omega t. Now if we simplify this, so from there we can do an analysis where we take the break that down the cos omega c plus omega term, and we get a plus I cos omega t into cos omega ct minus I sin omega t sin omega ct, and this this will give rise to a single cosine term where this angle psi d is given as tan inverse of this. So if we assume that a is much greater than I, then we can ignore I cos omega t. So we have, because the amplitude, carrier amplitude will be much greater than the noise power, so we will get tan inverse I sin omega t by a, and which is given as sin omega t by theta approximately. Now so here we see that we have to define something. When there is a noise, we have to define something called a figure of merit. This figure of merit is something which determines how well the signal is, like how less the signal is sensitive to noise, how stable it is with respect to noise. So what is the figure of merit? The figure of merit has been defined as the output SNR to the input SNR ratio. So for a FM, we can derive that the output SNR and the input SNR are given like this. If for a FM signal, so output SNR is given as this, and input SNR is given as this. So when we do output by input, we get 3 kf square p by w, where kf is the modulation constant, the frequency constant. So this kf is basically something that converts the message signal into a frequency. So the frequency deviation, it is the delta f is equal to kf mt. So kf is the proportionality constant between the frequency deviation and the message signal. So this is the figure of merit. Now The figure of merit is 3 kf square p by w square. Now 3 kf square p by w square, you can simplify this, where w is like the bandwidth, so you can simplify this as 3 by 2 beta square. So this is something that is used mostly, 3 by 2 beta square as a fmx square figure of merit. Now we will go to the problems. So the first problem is, which of the following statement explains why FM is preferred over AM in communication systems? So in the previous, like in the early years of radio, AM signals were used. Like the government All India Radio broadcast used AM signals. Then came FM signals, but FM signals were much shorter in range. But FM signals were much shorter in range. So as they used higher frequency, so they were much shorter in range. So the FM signals, like unlike AM signals, were not nationwide, but instead restricted to a particular city. So then gradually FM signals have replaced AM signals, and one of the key reasons why FM signals have replaced AM signals is the robustness of FM signals with respect to noise. So with respect to noise, the FM signal detection performance, demodulation performance does not degrade as sharply as AM signals. So FM signals are less susceptible to noise and distortion from nonlinear channels. So that is the correct answer. And why is that? Because in amplitude modulation you have something like this. So intuitively, for amplitude modulation you have something like this. Here the message signal is present in the amplitude itself, so the amplitude or the power is getting altered. So the noise also affects this power, and because the noise affects this power, so that a detection is directly affected by the presence of noise. Whereas in FM, the amplitude and hence the power of the signal is kept constant, and only the frequency or phase of the signal changes. So this can indicate that this ultimately, whatever the change in frequency may be, because cosine is bounded, cos theta is between 1 and -1. So whatever fluctuation this fluctuation in frequency can do, it will be restricted to -1 to +1. So the fluctuations due to noise is much less as compared to amplitude modulation, where the fluctuation can be from -infinity to +infinity. Fluctuation can be anything. Here fluctuation is between -infinity and infinity, means it can fluctuate to anywhere. Whereas here the fluctuation is between -1 and +1. Thus, because the fluctuation is much more limited, so as fluctuation limited, hence noise performance is more robust for FM. Performance is more robust for FM. Okay, which of the following is true regarding the figure of merit of an FM signal? So, is it always less than 1? This one translates to FOM less than 1. This one translates to same thing, that FOM can never exceed 1. So it is FOM less than equal to 1. This one is FOM can be greater than 1, and this one is FOM is equal to 1. So FOM is given as 3 by 2 beta square. The figure of merit of Fm is given as 3 by 2 beta square, where beta is the frequency modulation index. So beta being the Fm index, the Fm is given as 3 by 2 beta square. Now, for beta is nothing but delta F is equal to beta into mt. So this beta does not have any restriction because it is something that is converting frequency from volts. So beta has no restrictions. Beta can be anywhere in the positive number scale. So 3 by 2 beta square can also be anywhere in the positive number scale. So since it is anywhere between the positive number scale, the FOM which of the following is true. So it can exceed 1. So it is not less than 1, it is not greater than 1, it can be or like it can be greater than 1, it can be less than 1, it can be any real positive real value. But it will of course be a positive value because figure of merit is the ratio of two positive quantities, SNR output and SNR input. Next, what is the purpose of pre-emphasis filter and in FM transmitter? So this brings us to a new concept called pre-emphasis and de-emphasis filter. So first we will go to pre-emphasis filter. So we will come to the next concept, which is pre-emphasis filter, de-emphasis filter. Now, when you expect strong presence of noise in a particular band, what you want, the concept of pre-emphasis is that you will add extra signal power in that particular zone so that the effect of the noise power is throughout constant. So instead of sending something, say we are having a signal like this. Now we are expecting noise to be present in this region. So if we do not do pre-emphasis, there is a say negative noise, then it will fall like this, then it will again rise like this. So this is without pre-emphasis. Now, in pre-emphasis, what you are doing is you are anticipating the presence of noise. In pre-emphasis, you you are anticipating the presence of noise and compensating beforehand. So this is a pre-emphasis de-emphasis filter. So what you do is you take something like this. So there is a signal like this. So you compensate beforehand. So what you do is you take like this and you are expecting noise in this region. Say. So you are boosting this region like this. Now this much amount of depression it was the noise was creating. So you have raised the signal already by that much amount. So it is pre-emphasized. Pre-emphasized signal. Now if there is noise, if noise acts on it, you will have something like this. So here the depression is getting neutralized by the noise and you are getting the flat tone. So that is pre-emphasis. Now we have done the concept of pre-emphasis. We have to look for the implementation. So the higher the frequency modulation in FM, the greater the effect of noise. For higher modulation, this effect can be reduced by increasing the value of the measurement factor. This can be done by increasing the frequency delta F. Okay, so basically in pre-emphasis circuit, you are increasing the value of the higher frequencies. The process of optimizing the frequency components of a signal to improve the SNR. Therefore, the higher amplitude of the modulation signal, the more we can improve its ability to resist the noise of modulation. Yes, so we will boost the amplitude of the signal. So how do we implement pre-emphasis filter? We implement pre-emphasis filter using a high pass filter. So a pre-emphasis filter is basically a high pass filter because we are boosting the higher frequencies. So is usually implemented as a high pass filter like this. And to control the current, there is a capacitor, and to unload, there is another capacitor. টিসিএস রিসার্চ সিএসসি ছাড়া তো দেয় না, আমাদের ডিপার্টমেন্টে দেয় না। সিএসসি তেই দেয় টিসিএস রিসার্চ, আমাদের ডিপার্টমেন্টে দেয় না। কাউকে কোনোদিন পেতে শুনিনি আজ অব্দি। কেন বেচারাকে টোপ দিচ্ছিস? পালাতে চায় পালাতে দে না। তাহলে বি প্রিপেয়ার্ড ফর 37,000। So for the next part, so this is a high pass filter. Now this high pass filter will be tuned to a particular frequency, and it will emphasize that particular frequency element. So here you can see that from 0 dB it is not here. From 0 dB gain in up to 2122 hertz there is 0 dB gain, so there is no emphasis being done. After that there is an emphasis or 6 dB per octave slope. So here there is a gain in this region, there is a gain for 30 kilohertz bandwidth. After 30 kilohertz it again flattens. So there is a particular response of pre-emphasis filters which is like this. So first it is at 0 dB, there is no gain, it starts having a gain and it continues having a gain for a particular region, then it goes flat. So in a particular region only there is a gain. So this region, so if we add a pre-emphasis filter, say PEF before FM, then we will boost certain parts of the frequency which is most susceptible to noise, and thus we can cancel the effect of the noise. Now if the noise is not such that it not that heavy, such that it can completely out completely cancel the effect of pre-emphasis, so the noise is not that strong so that it can cancel the effect of pre-emphasis, then we have to do a de-emphasis to remove this effect of pre-emphasis. So here next we will have a de-emphasis filter, and a de-emphasis filter will be exactly the inverse of a pre-emphasis filter. De-emphasis filter is the exact opposite, or rather than opposite, I think the term is inverse of a pre-emphasis filter. Next, so if a de-emphasis filter is like this, then the corresponding a pre-emphasis filter is like this. Then the corresponding de-emphasis filter will have characteristics like this. So here there is a 0 dB, then we will have a inverse gain up to this point and then flat. So this is a de-emphasis filter. So it undoes the effect of a pre-emphasis filter, and it is situated at the receiver, whereas the pre-emphasis filter is situated at the transmitter. With that in mind, let's tackle the question. So what is the purpose of a pre-emphasis filter in FM transmitters? Is it to boost low frequencies? Is it to attenuate high frequencies? Is it to boost high frequencies, or is it to filter out noise? So it is a high pass filter, so it will boost high frequencies. It will not attenuate them, neither will it boost low frequencies. And noise filtering cannot be done using a filter, a pre-emphasis filter. So it is option C. Now one disadvantage of this pre-emphasis filter is the amplification of 1 by F noise. At higher frequencies, They are due to the parasitic capacitances. There is a special type of noise called the 1 by f noise. This 1 by f noise, as you can guess from the name, will increase with increase in frequencies. Sorry, with will increase with yes, sorry, 1 by f noise. Okay, no, 1 by f noise. Huh. So it is low in high frequencies, but because of the high pass filter, it still gets boosted. Due to the presence of a pre-emphasis filter. Next question. State whether the following is true or false. The question is that the de-emphasis filter used in FM receiver is a type of high pass filter. So, de-emphasis filter is inverse inverse of pre-emphasis. So, so if de-emphasis filter is inverse of pre-emphasis filter, and pre-emphasis filter is HPF, then emphasis filter will be LPF. So de-emphasis filter being high pass filter is a false statement. So it is false. De-emphasis filter is a low pass filter. Next, state whether the following statement is true or false. The figure of merit of narrowband FM is greater than that of wideband FM. Now, as you can imagine, that the figure of merit expression is inversely proportional to the bandwidth, because as bandwidth increases, you are susceptible to more types of noise and more magnitude of noise. So the more bandwidth you have, the more you are exposing yourself to noise. So your figure of merit, which is your robustness to noise, will of course reduce. So we can say from intuition that FOM is inversely proportional to bandwidth. But the exact expression is given here, 3kf square p by w square, where kf is the frequency to message signal conversion constant. So it is the frequency to voltage conversion constant. Frequency to voltage conversion constant. P is the power, transmit power, and W is the bandwidth. So it is 3kf square p by w square. So as you can imagine, as bandwidth will increase, FOM will decrease. So FOM of narrowband FM will be greater than FOM of wideband. So the statement that the figure of merit is of the narrowband FM is given in words, but actually here it is given that the increasing bandwidth will result in better noise performance. But as we can see from the lecture material, that the figure of merit is inversely proportional to the bandwidth of the signal. So I would say that you ignore this. The correct answer will be A, true, because FOM is inversely proportional to W square. Next, the operation of click noise in communication system is primarily observed in now AM system, FM system, both AM and FM on. So first we have to understand what is click noise. So click noise in signal processing is a transient short duration impulsive disturbance that corrupts the signal. So click noise happens suddenly and it will be a very short duration but high magnitude impulse. So a click noise is looks something like this. So click noise So click noise is something which has a short duration, high magnitude, short duration, high magnitude impulse signals. Short duration, high magnitude impulsive noise. So it will look something like this. This is a click noise. Now, the shorter duration in time implies wider bandwidth. Shorter duration in time will imply a wider bandwidth. So this will imply something like this. So the wider the, sh- the wider bandwidth will usually affect the FM system, because in FM system this there are sudden changes in frequency and phase, and this sudden change in frequency and phase creates this kind of click and pop noise, and this will affect the FM because the FM also is relatively wideband as compared to AM, so it will affect the FM system more severely. So the correct answer for this is FM system. The occurrence of click noise is typically observed in FM systems. The phenomena occurs due to certain phase or frequency shifts in the transmitted signal, because sometimes the voltage value is discretely mapped to frequency. So positive voltages give plus F, negative voltages give minus F, like that. So if it is discretely mapped to frequency, a small change in voltage might switch over from positive to negative, and that will lead to a drastic change in the frequency. So like in frequency shift key you observe. So this kind of thing is usually observed in FM systems. In which of the following modulation schemes a decrease in bandwidth results in lower value of figure of merit? Okay, this is we have discussed earlier, so we will skip this because this has an issue. Now, for a tone signal, mt equal to cos omega mt equal to cos omega mt, find out the minimum value of FM modulation index beta such that the figure of merit of FM exceeds that of TSBSC. So there is a tone signal, that is, it contains a very single tone, a single frequency, and Find out the minimum value of FM modulation index beta such that the figure of merit of FM exceeds that of DSBSC. So the figure of merit of tone signal for FM, the figure of merit for FM is given as 3 by 2 beta square. The figure of merit of FM is given as 3 by 2 beta square. Okay, so figure of merit of FM is 3 by 2 beta square, and the figure of merit of DSBSC is 1, which has been shown earlier in noise analysis, week 7 I think. So 3 by 2 beta square has to be at least greater than 1. So this means beta square should be greater than 2 by 3, or beta should be greater than root under 2 by 3. So root under 2 by 3 is the answer. So it is root under 2 by 3. Option C. Now the pre-emphasis filter is 1 plus f. So what will be the pre-emphasis inner, if the transfer function of pre-emphasis filter is given as f equal to 1 plus f, then the transfer function of de-emphasis filter is. So de-emphasis filter is simply the inverse of the pre-emphasis filter. So if the de-emphasis filter is this, it will be the inverse of the pre-emphasis filter. So the pre-emphasis filter is 1 plus f. So the inverse of that will be 1 by 1 plus f. As simple as that. So the correct answer is 1 by 1 plus f. Now AWGN, if an AWGN with the two-sided power spectral density n naught by 2, that is the AWGN is given like this. AWGN means it is white. It is present in all frequencies equally on both sides because it's a two-sided AWGN, and the value of that noise is n naught by 2. Now, and it is passed through a filter with transfer function 1 by 1 plus f square. What is the total power of the noise after filtering? So it is the noise is this wf equal to n naught by 2, and it is passed through a filter which is given as 1 by 1 plus f square. So hf equal to 1 by 1 plus f square. So the output yf will be mod hf square wf. Now mod hf square means 1 by 1 plus f square whole square, and this is n naught by 2. Now the power P is the integration of yf df. So because yf is the PSD of output, as yf is the PSD of output, just integrate the PSD over the entire bandwidth and you get the noise. So it is minus infinity to infinity n naught by 2 df 1 plus f square whole square. So this is an even function, so integrating it will lead to an odd function odd function means at infinity and minus infinity it will have the same value. Sorry, it will have the negative value, inverse value. So if you add them, you will get two times. So if the integration gives I, the at plus infinity it will give minus I at minus infinity. So I minus minus I will give you 2I. So ultimately it is n naught 0 to infinity df 1 plus f square whole square. Now this comes out to be pi by 4. So it is pi by 4 into n. This is a known integral, that 0 to infinity dx by 1 plus x square whole square is pi by 4. So it is pi by 4 into n naught. So we are done with noise analysis of FM. Next, we will tackle some objective questions regarding frequency modulation. Let's take these questions one by one. Not this one. Okay, so let's start. The modulation, a carrier signal of 100 megahertz is modulated using a sine wave whose frequency is 75 kHz with a deviation of 50 kHz. So, for the first question, a carrier signal of 100 megahertz is modulated using a sine wave whose frequency is 75 kilohertz with a deviation frequency of 50 kilohertz. So, what is the modulation index? The modulation index is delta f by fm. So, the deviation is 50 kilohertz and it is based on a message signal whose frequency is 75 kilohertz. So, it is precisely 2 by 3 or 0.667. So, the correct answer is 0.667. Now, NBFM bandwidth. For NBFM, the bandwidth is 2 into f plus fm plus delta f. Now delta f is beta fm, so it is 2 fm beta plus 1. So correct answer is 2 fm beta plus 1. Next, what is the basic difference? The basic difference between NBFM and AM. Now NBFM and AM have the same bandwidth, the same frequency deviation, but the lower sideband for NBFM looks like this. So NBFM looks kind of like this. There is a carrier and there is a upper sideband. So LSB is reversed, USB, and this is carrier. Now here the LSB is like this. This is AM. This is NBFM, and this is AM. So the only difference is the algebraic sign reversal of the lower sideband. So correct answer is this. Okay, here for narrowband FM, this will be 2 FM, and for wideband FM, it will be 2 FM beta plus 1. Narrowband FM has the same bandwidth as amplitude modulation, which is 2 FM. Now, next question. A 12 megahertz carrier gets modulated, this is by a sine signal with a frequency of 500 hertz, bearing frequency deviation delta f equal to 50 hertz. Now, here delta f is 50 kilohertz, which is 50,000 hertz, and FM is 0.5 kilohertz, 500 hertz, which is 0.5 kilohertz. Now, this is 50 and this is 0.5. 50 is much greater than 0.5. So, delta F is 100 times FM, so it is much greater than FM. Implies this is a wideband FM. So, it will be 2 into delta F plus FM. So, it will be 50.2 into 50 plus 0.5. 50 plus 0.5 is 50.5 into 2. If you do, you will get 101. So 101 kilohertz is the bandwidth. Now, based on modulation index, FM is classified as either narrowband or wideband. So it is both B and C. Next, in NBFM, the modulation index. For NBFM, delta F is less than FM. So beta is less than 1. Modulation of source signal with multiple frequencies components. Modulation of the source signal with multiple frequency components is called multitone modulation. Modulation index will be greater than 1 in wideband frequency modulation. The transmitted power is independent of modulation index. So the transmitted power is independent of modulation index. That means the modulation is only happening in the frequency or phase. So it is either frequency modulation or phase modulation, but not amplitude modulation. Next, noise immunity is superior in frequency modulation, as we have discussed earlier. Now, modulation index in frequency modulation is proportional to modulating frequency it depends only on the frequency deviation, which is the message signal, the modulating signal. So it is delta F by Fm. So it is Kf mt by Fm. So it depends on the message signal and the modulating frequency, modulating signal and frequency. This is the modulating signal and this is the modulating frequency. So beta depends on this is the modulating frequency. So the beta depends on both the modulating signal and the modulating frequency. So it is both A and B. Next, in dash, angle is directly proportional with the integral of modulating signal. So it will be phase modulation or frequency modulation, because in frequency modulation the frequency is varying with the message signal. The phase is the integration of the frequency. So here phase is varying as k integral kfmt dt. So in FM phase is varying in FM phase is varying as integral of the message signal, not the message signal directly, but frequency is varying with the message signal directly. Whereas in PM or phase modulation, you have phase is varying with the message signal directly, whereas the frequency is varying as the derivative of message signal. So it is here the integral, if it is varying with integral, then it will be frequency modulation. Now departure of maximum instantaneous frequency from carrier frequency is known as frequency deviation. Sideband present in frequency modulation are infinite, or at least they are very large. Total variation of frequency from its low to high point is termed as the frequency deviation, because it is the variation of the frequencies. Or in FM signal, the amount of frequency deviated is dependent on. So what is delta F? Amount of frequency deviated is delta F. What is delta F dependent on? So delta F is simply Kf mt. So here it depends only on the amplitude and phase of the modulating signal. So you can say amplitude. If you take the magnitude, it is only amplitude. Sidebands in FM are controlled based on selected. So what is the sideband in FM controlled by? The selected modulating frequency. Maximum deviation is due to transmitter design, transmitter configuration. That is it. Okay. Dash is used to estimate the bandwidth of FM signal. Carson's rule. So the correct answer is Carson's rule. Carson's rule says bandwidth is twice the frequency deviation and message signal sum. Next, the spectrum of NBFM is similar to the spectrum of amplitude modulation, and the Carson's rule for calculation is 2FA, 2 delta F plus Fm, but also 2Fm beta plus 1. Both are correct. So the delta F in Carson's rule is peak deviation in frequency. What device is used to convert the received FM signal to voltage? So if you have a particular frequency and you want to convert it into a voltage, you need a phase lock loop. And an oscillator does the opposite. It converts a voltage into a particular frequency. Other than frequency discriminator, a phase lock loop can be used for FM demodulation. FM is normally used above 30 MHz. Two common applications are communication and FM radio. An FM receiver consists of amplitude limiters. The purpose of the amplitude limiter is removal of amplitude variations. So it removes noise. Circuit consisting of differentiator allows. Okay, now a differentiator in time is a high pass filter in frequency, because if you do a differentiation in time, it is equivalent to multiplication by frequency in frequency domain. So dxt dt, the Fourier transform, as we know, is sxx. S, or you can write f 2 pi f, j 2 pi f, j 2 pi f x f. So multiplying by frequency is, so you have fxf. Now this will be a high pass response, so it is high frequencies. Now that circuits are used in FM. Pre-emphasis, de-emphasis circuits are used in Okay, the purpose of guard bands in FM is to prevent adjacent channel interference, increase bandwidth, increase noise. So, for guard bands, what they do is, say that you are transmitting one FM signal here, and like this, you are transmitting one FM signal here, and you are transmitting another FM signal here. So, there has to be some kind of a gap. This gap is called the guard band. If this gap is not there, then there will be interference. If this gap is not there, then there will be interference between this channel FM and this channel FM. To prevent adjacent channel interference, we use guard bands. FM broadcast requires dash max bandwidth for commercial uses. I think this will be 100 kilohertz. 200, okay, 200 kilohertz is the maximum bandwidth. These are general knowledge questions. So, to ensure the input signal amplitude in FM discriminator is maintained constant, what is used? So, differentiator is a high pass filter. Envelope detector detects the envelope or the amplitudes. A limiter detects the amplitude. Rejects variations in amplitude. It limits the amplitude to a certain level. So limiter is used to ensure that the input signal amplitude in FM discriminator, which is used to demodulate FM, has constant input. So it is limiter. AFC stands for automatic frequency control. What is the parameter constant in amplitude? It is in FM. It is amplitude. Amplitude is constant in FM. Phase and frequency vary. Pre-emphasis is performed before modulation, and pre-emphasis can be done to boost the voltage of the modulating signal. Modulation of signal at high frequency before modulation. So all of the above. So pre-emphasis is done to boost the voltage and at high frequencies, and it is done before modulation. What will be change in bandwidth of FM signal as the frequency of modulation increases from 14 to 28? So, assuming delta F is constant, the message signal is constant, so delta F is constant. So it is FM FM dash, and another is 2 delta F plus FM. So FM dash, so it is 2 into FM dash minus FM. FM dash is 28 and FM is 14. So it is 28. The characteristics of WBFM is wide bandwidth and also large frequency sensitivity. So both A and B. And characteristic of NBFM are both small kf and narrow bandwidth. A PLL can be used as a FM demodulator because it creates voltage according to the frequency that is present. So the change in in FM, the voltage of the message signal is encoded in the change in frequency. So the frequency so PLL generates a voltage corresponding to that frequency, proportional to that frequency. So we can say that PLL is being used as a FM demodulator because whatever the delta F is, PLL will generate a voltage corresponding to that delta F, which can be treated as a MT or message at the receiver. So it is the demodulated message of the receiver. Okay, so I think that will be all for today. So this concludes today's class on noise analysis of FM. Next week there will be the last class, week 12, on sampling theorem, I think. So Tuesday 6 p.m. Thank you.